Okay, so we will start to talk about the radiation characteristics of the real surfaces. Till now we have covered black bodies. For the real surfaces we have the different notations because the real surfaces are more complex than the black bodies, therefore we have additional notations. The first thing here for the real surfaces is the rate of heat transfer with unit of watt, which is shown as Q dot. And we have the emissive power with unit of watts per meter square. It is also flux because it is per unit area, and which is shown as E. We have the irradiation or incident heat rate, that is watts per meter square, again with unit of the which shown notation as G. And the J is the radiosity or net outgoing heat rate with the same unit and shown as J. If you have a picture here, we can show the values here. There is an incident radiation which is G, and we have some part of it which is absorbed with some coefficient of alpha, so alpha into G, and some part is reflected. This doesn't have any unit, there is no unit here, there is no unit here. Some part of it is transmitted, which is tau, and some part is reflected, which is rho into G. And additional to this one, we have also the emission from the surface, which is shown as the E. And this emission is part of, this one comes from the internal energy, this one is part of internal energy, but this one not part of internal energy. Okay, this one just strikes and reflects, and the radiosity will be sum of the emissive power plus the reflected one. Okay. And then we have the intensity, which shows the strength of the radiation, which shows the strength of the radiation. This is called intensity. And we have also some subscript is E, which says that it is emitted, and the I, which is incident, and the lambda, which is the monochromatic or per one wavelength, and the angle, which is angle in one direction, T for one fixed temperature. Okay, and if we can also have the subscripts, which is the E, again the emitted, I means it is incident, and the ref means it is reflected, etc., because we could have different absorbed and transmitted here too. And to give one example for the subscript, say that I have the emissivity as a function of the lambda. Okay, and it means that this one is called spectral emissivity. It means that if I give you the lambda given, you can find the emissivity. Okay, or emissivity is given as, for example, lambda square plus lambda. It is possible. Okay, but if I say that emissivity itself, then it is not function of the lambda. If I give you lambda, you cannot find emissivity. So you will have some fixed value for 1, or you could have the 0.1, or you could have the 0.2. If you show as a graph, E lambda versus lambda, you will have something like this one. Okay, but if I say the E value here, epsilon value, not E, epsilon value here, then it is not function of the lambda. You will have just one epsilon, one fixed epsilon. Similarly for epsilon temperature. Okay. If I give you the temperature value 25 degrees Celsius, you can find the epsilon. But if I say that epsilon itself, it doesn't matter which temperature it is, because it is averaged for all the temperatures. Okay. Average value for any temperature, average value for any lambda, but here it is function of the lambda. It depends on the lambda, it depends on the temperature. Now another thing about the real surfaces is that they have the emissivity epsilon, but for black bodies epsilon is 1. They have the absorptivity, but for black bodies absorptivity is 1. They have the transmissivity, but for black bodies transmissivity is 0, but they have the reflectivity, which black body has a reflectivity of 0. Therefore, the real surfaces is more difficult than black bodies. They don't have the emissivity of 1, they have the emissivity of less than 1, greater than 0, in the range of 0 and 1. Similarly for other properties. This is the first thing about the real surfaces. Another thing about the real surfaces is that the radiation here is not function of temperature only and the lambda, but it's also function of the direction. Okay? It depends on which direction you are taking the radiation. This is the second thing about the radiation. Now we'll talk about the intensity of the intensity in real surfaces, which is very important. We have said that it shows the strength of the radiation. For example, if you have a lamp here, okay, this lamp emits rays in this direction, and these rays have different emissive intensity here, and it has this different intensity here, where I1 is greater than I2, because here you have more strength. This is the first thing. And another thing about the intensity is that it is function of the direction. If I take the intensity here, you can see it is bright. If I take another point here, you have different intensity, because you have different angle here. Okay, different angle and therefore different intensity, function of the direction. And it's also function of the temperature, because say that I have two surfaces, surface 1 and the surface 2. This one is at T1, this one is at T2, which is greater than T1. If you put your hand over it, you will feel the different strength at each location, at the same location, which is R, because this one has more temperature than that one. Therefore, the intensity is the function of the temperature. And it is also the function of the lambda, which is the wavelength, because the wavelength itself is function of temperature. So if you have different wavelength, you will have different temperature. With different wavelength, different temperature. Okay. Therefore, the real surfaces is more complex than the black bodies. The properties depend on the lots of factors that are considered. Now the time is to introduce the definition of the intensity. The intensity is the differential rate of emitted radiation, okay, which is dQE, per the area DAN. So that this part is very important. We will talk about per wavelength and the per solid angle. We'll talk about this one too. Okay, now firstly, differential solid angle. What is differential solid angle? In 2D, let's say that this one is circle, this one is 2D circle, and it has full angle is 2 pi. Okay. If I want to find the circumferential length of this circle, it will be 2 pi into r. This one is the radius of the r. This one is for 2D. If I take the 3D, for 3D I have sphere. Okay. Surface area of the sphere is 4 pi r square. Okay. And here we are define the angle as omega, and it is 4 pi. Okay. And here we define the angle as 2 pi, it is L by R, but here it is AS by R square. Whatever role this angle plays here, 2D angle, okay, the same role is played by this 3D angle. It shows the fraction of the surface area of the sphere, and here it shows the fraction of the circumference of the circle. For example, if I take a circumference here at 30 degrees, then the L will be equal to 2 pi r divided by 12. Then 2 pi by 12 is a 2D angle. Similarly, if I take some part hemisphere, for example, hemisphere, then it will be AS by 2, then here omega will be 2 pi. Okay. In 2D we are showing the angle something like this one, but in 3D we are showing angle something like this one. Okay, similarly here. Okay. Or if you have a point source, this one is point source, it can be, for example, laser. Okay. Laser, the rays are emerging from the laser, and then you are taking omega something like this one. Okay, this is the definition of the 3D angle, which is called solid angle and shown as omega. When we talk about differential solid angle, we are taking it as d omega. Okay. That is the first definition. And the second definition is that DAN. What is that? DAN is, say that I have a surface which is hot. Okay, this one is the original surface. This original surface emits radiation in all directions. Okay, in all directions. And if I connect directions that this surface emits radiation, it can be spherical or it cannot be spherical. It is possible in so say that this is the surface I've taken at a distance of Z or R. This is the field of emitted radiation. Okay. At this location, you will have this amount of emitted radiation. Similarly to this one, if I take location here, I will have this amount of radiation, then here I will have this amount of radiation. Say that I am trying to find what is the differential area on that surface. For example, at this surface, this one is 3D surface, I am trying to find what is that differential surface, okay, differential element on that surface. Why is it important? Because the intensity emitted from this surface, the strength of radiation, it changes as a distance, it changes as an angle, because at this angle you have different radiation, at that angle you have different radiation, and it depends also on the lambda. To find the small values, elemental values, that all of the properties are constant, I will take the small values. For example, I will take the small wavelength, I should take the small element, I should take also small angle. So for that case, I am taking a small differential element here, elemental area, and to find the intensity that falls on that area. Okay, this is the purpose of our mathematical calculation. Okay. And to find that that surface here, DAS, okay, we are using spherical coordinates because it is easier to analyze. Okay, because it is easier to analyze. This is the first definition. Another definition can be that, say that I have a surface something like this one. Okay, this surface emits radiation. I have another surface here, and I'm trying to find what is the radiation that hits this surface. Well, first step could be, I will take a small differential element here. Okay. Then from differential element, I will find what is the emitted radiation that is incident on this surface, and then I will integrate for overall surface. Okay. Therefore, differential element in real surfaces is very important. And DAS here, and you have the DA. Okay. If you go back to spherical coordinates, you have the DAS here, DA here, which is the original area. This DAS, if you notice that this one is the area, part of the area, DAS is part of DA when viewed at an angle of phi and theta and r. So this DAS, if I view from here, I see the DA as DAS. Similarly, this one is DA. If I look at DA from here, I will see something like this one. Okay. Therefore, DAS becomes the projected area of DA. So this DA has two components. One is here, the other one is here. This one is 90 degree. And since this angle is phi, and therefore this angle will be also phi. DAS becomes DA cosine phi. Okay. This is important. Now let's find DAS in spherical coordinates. Here, this one is DAS in spherical coordinates. DAS can be found, if you remember from differential calculus, if you have a radius here, if I take a small angle d theta here, the small distance dl, the length can be found by r d theta. So the radius and the angle is enough to find the length of this piece. And similarly here, I have DAS, it has two pieces, one is dy, the other one is dx. Okay, I'm trying to find what is dx and what is dy. To find the dy, I firstly introduce the radius. To introduce the radius, there should be circle. The circle is this one, if you notice that. Okay, this one is the circle for dy. If I use different color, you can see it better. This one is the circle for dy. Okay. This circle has a radius of r, which is the same radius as the sphere. Again, the r here, we are taking a small element here, similar to this one, and the small angle over here is the phi angle, which is d phi, because phi goes in that direction. Okay. D phi, therefore dy becomes r d phi. Now comes dx. For dx also I will take the circle here, so the circle of dx is this one, and the distance for that dx will be this part, but this distance is not the radius, but this distance is that the angle is phi, therefore you have the phi angle here, the same phi, and this distance here is r sine phi. Okay, because you are looking for, if this one is 90 degrees, you are looking for, this one is 90 degrees, we are looking for the component of r in that direction, which is r sine phi. So dx becomes r sine phi into the small angle here. This small angle is theta, because in that direction you are going as d theta, therefore it will be d theta. And the das will be equal to r square sine phi d theta d phi, which is equal to dx and dy. And dan here is the same as das. Okay. So what is intensity? Intensity is the differential rate of emitted radiation. In that direction, radiation is emitted because this part is hot, and from that hot surface we are emitting radiation. That the intensity is defined as that emitted radiation divided by the solid angle, and also das, small surface, the area viewed from that direction, and into the lambda. And the solid angle d omega will be equal to das divided by r square, and therefore it will be sine phi d theta. Okay. This is the first important thing about the real surfaces, which will be used in our next slides very often. Okay, so the spectral emissive power and the total emissive power. Spectral emissive power is E lambda, and the total emissive power is E. Okay, so we should find these quantities. Firstly, I will start from the easiest one, which is the total emissive power, E. The unit of this one is watts per meter square. Okay, and it is emitted radiation per area and per second. Rate of or emitted radiation per area. Okay, rate of Q dot emitted per area. Okay, so to find that quantity, we will introduce the definition of the intensity. That intensity, i.e., emitted intensity was equal to differential rate of emitted radiation by this quantity. So let me write it here. The differential rate of emitted radiation divided by das, d omega, and d lambda, that was equal to I emitted, which is function of the lambda, theta, phi, and the temperature. And first, to find the total emissive power, I should find the emitted radiation per area. But in this case, which area? Do we mean the first area or the second area? Here we are taking the first area or original area. This one is A, original area, okay? Because the emitted radiation from the surface, when we say, we are talking about the original surface. And then E quantity will be the small e. Small e will be equal to dq dot divided by the dA, original area, and now we know that das is component of the dA in the direction that I have viewed, phi, cosine phi. Therefore, this quantity will be equal to I emitted, which is function of lambda, theta, phi, and the temperature, multiplied with the cosine phi, and multiplied with the d omega, which is sine phi d theta d phi, and multiplied with the lambda. Okay, that is the differential rate of total emissive power. But if I want to find the total emissive power, and then it will be that integral of this quantity, and to integrate that quantity I will integrate three quantities here, which is theta, phi, and the lambda. For the theta, the integral is taken for overall angles, which is 360 degrees. For phi, it will be 90 degrees. Okay, then for theta it is from 0 to pi. For phi it is from 0 to pi by 2, and for lambda it is integrated for overall wavelengths. Okay, so then you will have I lambda theta phi and the temperature emitted cosine phi sine phi d phi d theta d lambda. That is the definition of the total emissive power for real surfaces. You should know this function, you should know these two functions to integrate that quantity. So I know that for black bodies, a black body is sigma t to the power of 4, which is very easy and simple. But for real surfaces, you can see the quantity here. Now let's calculate the spectral emissive power, which is the E lambda. Okay, to find the spectral quantity, so I will introduce again the same thing here, emitted lambda theta phi and the t. That quantity is equal to dQe divided by dAs, which is dA cosine phi into d omega and into d lambda, and dE lambda is equal to dQe divided by dA, again the original area, into d lambda. So I can write this one as dE lambda is equal to I emitted, which is function of the lambda theta phi and the temperature, into d omega, and there is cosine here, cosine phi d omega, and let's write d omega also in general form. So cosine phi, write it. So you will have the cosine phi d omega is the sine phi d phi d omega, and the d lambda we don't need it because we are looking for per wavelength, and the phi goes from 0 to 2 pi, 0 to pi by 2, and the theta goes, so it is theta, d theta, and the theta goes from 0 to pi 2 pi. Okay, that is the dE lambda. To find that is dE, sorry, that is E lambda. Okay, this one is the E lambda because I have integrated it. Okay, but this quantity over here, it is dE lambda. Okay. That is the definition of the spectral emissive power. Spectral emissive power of the black body is the pi into I temperature black body, which is function of the temperature. And now comes the emissivity, and we have three emissivity type classification of emissivity. We will start from the easiest one, which is total spectral emissivity, that we always see in heat transfer, which is between 0 and 1. And this total hemispherical emissivity is the E, the total emissive power of the real surface divided by E black body. And I've said that real surface, and this one is sigma t to the power of 4. And the hemispherical emissivity, or spectral hemispherical emissivity, similar to this one, spectral emissive power, so it will be E lambda. Okay, this one is the same as here, we have divided by E lambda real by E lambda black body. Okay, and E lambda real divided by the pi, so I temperature black body. It's function of the temperature, or you can write in full terms. It will be that you can integrate from 0 to 2 pi, which is for the theta, and for the phi we will integrate from 0 to pi by 2. It will be that I, which is function of lambda theta phi, and the temperature, which is emitted, cosine phi sine phi, and the d phi d theta. Okay, divided by the similar thing for black body, which is simple, p I temperature black body. That is the hemispherical emissivity or spectral hemispherical emissivity. It depends on the lambda. Now comes the spectral directional emissivity. It is dependent on the lambda, it is dependent on temperature, it is dependent on the phi, and it is dependent on the theta angle. So it will be very easy. It will be I lambda temperature phi theta emitted real body divided by I emitted lambda temperature phi theta black hole. This is the definition of the emissivity. But most of the time we are using this quantity over here. Okay. And now we are going to talk about the other properties of the real surfaces. If we have the diffuse surface, and diffuse surface means that the radiation in all directions is the same. If you put your hands here, you have the same radiation. If you put your hands here, you will feel the same radiation. If you put your hands here, you will feel the same radiation. In other words, radiation is independent of the direction, and therefore it is called isotropic radiation. Another body is called the gray body. We know black body, and now there is gray body. And the gray body is that the emissivity is independent of the lambda. Whatever lambda is, the emissivity is constant. And there is semi-gray body. Semi-gray body means the half of the properties of the gray body, and in this case you have the emissivity that is constant, but it is not constant for overall the lambdas, but it is constant for some range of the lambdas. If you look at it here, so it is constant in this range and it is constant in that range. Okay, and there is diffuse gray body. Diffuse gray body means that the epsilon is not function of lambda. Okay, epsilon is not function of the directions or angle, therefore whatever left is that epsilon is function of the temperature only. These are to simplify the problems, and also we have some materials that carry these properties. And if you go back to our first slide, and we said that there is an incident radiation on the body which is G, and some of it is reflected, some of it is absorbed, and some of it is transmitted. So then G is equal to reflected portion plus absorbed portion plus transmitted portion. If we divide all of them by G, you will have 1 is equal to rho plus alpha plus tau. Okay, which is very important for radiation problems. And there is also the bidirectional nature of the reflection, or dual nature. It is that if you have a surface, if it is the incident ray, if you remember from the optics, the incident ray creates an angle with the reflected ray which is equal with respect to normal. Okay, this is the normal and they are equal. This is called specular reflection, which is true for rough surfaces. But for smooth surfaces, if you have an incident radiation, that incident radiation is reflected in all directions at the same amount, okay, in a diffuse manner. And if you look at it, it is reflected in all directions at a diffuse manner, and these are called diffuse reflection. Therefore, for one incident reflection, you can have different possibilities, and it is called bidirectional nature of the reflection. And energy balance, we have said that alpha plus rho plus tau is 1, and if it is opaque surface, then tau is 0, alpha plus rho becomes 1 for the opaque surface, and if it is black surface, then rho is 0, then alpha plus tau is 1 for the black surface. If it is black and opaque at the same time, you will have alpha which is equal to 1. And now comes the spectral irradiation, which was G here, and the total irradiation. We'll start from the total irradiation, which is very easy. It is very similar to this part, total emissive power E, and now we are talking about the irradiation, and in this case we look for incident radiation intensity, and it will be a function of the direction as well as temperature and the lambda, and we will integrate it with respect to all angles and all wavelengths. Okay, and you will have 0 to 2 pi, 0 to pi by 2 and 0 to infinity, and this is for this total irradiation. And if you are talking about the spectral irradiation, and then you will take the spectral irradiation, lambda will be equal to 0 to 2 pi pi by 2, and you will have the same relationship here, but instead of lambda you will not have any, and d phi d theta. Okay. And now comes the total hemispherical reflectivity, which is rho is equal to g reflected portion plus g incident portion, or total g. Or the spectral, it could have the rho lambda will be equal to, so you will take I reflected portion intensity, and you will have the lambda, theta, phi, and the temperature. You will integrate with respect to angle only, and you will not consider this 0 to 2, but you will not consider the lambda here, and divide by the same stuff, and but now it will be I lambda, theta, phi, temperature. Instead of reflected you will have the incident. Okay, and the cosine phi, sine phi, d phi, d theta. Okay, that is definition for the reflected hemispherical spectral hemispherical reflectivity. And if you talk about absorptivity, instead of that one you will write alpha, instead of reflection you will write absorption, and here you will have the alpha, and here you have reflected, instead of the reflected you will have the absorbed. And similarly for the transmissivity, you will have the tau, instead of absorbed you will have the transmitted, and here instead of absorbed you will have the transmitted. That's the definition of the total and the spectral values. And most of the time you are working with these total values instead of the spectral values. Okay, so now I'm writing the Kirchoff's law for the total hemispherical case. So say that I have an object inside an enclosure. Okay, this object, size of object is much smaller than size of enclosure. Okay, and in that case, since the object size is very small, then whatever emitted radiation is from the object, write it, whatever emitted radiation is from the object, it will become internal energy of the system after multiple reflections. It is very similar to where we have a cavity here, incident radiation, and it reflects here, and it becomes internal energy of the system. Okay, similarly here. So therefore, the enclosure becomes black body. Okay, and this object, there is an incident radiation on the object, which is G, and this object emits a radiation which is E. If I write the first law for the object, then the object will absorb some energy and it will emit some energy. These two quantities should be equal in thermal equilibrium. Okay, that's the condition. In other words, the temperature of the object and the temperature of the enclosure are equal. And then we can write the G as, because we have said that black body, the enclosure becomes black body, sigma T to the power of 4, and the emissive power of the object, I can write this one as epsilon into sigma into T to the power of 4, because this one is the real body, there should be some quantity here, fraction, then alpha becomes the epsilon. Okay, that is the Kirchoff's law for thermal equilibrium bodies and one of the bodies in black body. And we can write this Kirchoff's law for some cases where the bodies are in equilibrium, but we should be careful. And the second case for the Kirchoff's law is that epsilon and alpha, since these are a property of the material, okay, since these are the surface properties, then it means that alpha and the absorptivity and transmissivity, so it means that absorptivity and emissivity is always equal when you are looking for the directional and the spectral case. Okay, this one is always true. Okay, and this one is for thermal equilibrium. Okay. And another thing is that is epsilon and alpha are equal in spectral terms. You can check for it, and we know that epsilon lambda is equal to, so the I, this one is the real body, into d omega cosine phi divided by I black body d omega cosine phi. Okay. So the question is it equal to the alpha, spectral alpha, that will be I absorbed. Okay, and this one is for the d omega cosine alpha and divided by I incident d omega cosine phi. Okay, question is when these two quantities are equal. So since the black body black body intensity is independent of the direction, therefore I can take it out of the brackets or bring inside the brackets integral here. So that means that I can write this one as I black body. Okay, this quantity as, so then this quantity becomes epsilon and becomes the lambda and theta and phi and the t. Okay, this is the left hand side, and for the right hand side I can write this one as, for the right hand side I know that alpha, theta, phi and the temperature and the lambda is equal to I absorbed divided by I incident, and instead of I absorbed I can write it as alpha into I incident. Okay, but when I say alpha I mean that theta, phi, t and the lambda is there. So if I can write the terms again here, it will be that, so the left hand side is epsilon and into d omega cosine phi. This one is the spectral and the directional, and divided by d omega cosine phi. The question is, are these quantities equal? So then it will be that for the right hand side I will write alpha and the incident intensity into d omega cosine phi divided by, so then I incident d omega cosine phi. Okay, are these two quantities equal? Then we should look for the equality conditions. The one is when these quantities are equal, it means that this I incident should be independent of the direction. So because if it is independent of direction, you can bring it here. If it is independent of direction, you can bring it here. And then since epsilon and alpha are equal at all conditions, then it means that these two quantities will be equal to each other. Okay. Then this is the first condition. Incident radiation should be independent of the direction. Okay, and the second condition can be, this is the first condition. For the second condition, let me use other color. So when these two quantities are equal, so in that case, if alpha and epsilon is independent of the directions, then it means that I can bring this one in front of the integral, I can bring this one in front of the integral, then this term becomes 1 and this term becomes 1, they are equal to each other. So it means that epsilon and alpha are not function of the theta and the phi. That is the second condition for the this one is the first. Okay, if it is there it is okay. Okay, if this one is there it is okay. It means it is either or. It's either or. Okay. And this one is for spectral directional emissivity and the spectral emissivity. For the total hemispherical emissivity, we have said that the enclosure is black body and that there is thermal equilibrium with each other. Okay, if we summarize what we have told till now, we have said that epsilon, lambda, theta, phi and the t, that is equal to alpha, lambda, theta, phi, t. This one is always, that's always true because this is the material property, and at the given wavelength and the direction and the temperature, the material has the same emissivity as it is absorptivity. This is always true. And we have looked for epsilon, lambda, alpha, lambda when they are equal. We have said that two cases. One is that incident intensity that falls on the object is not dependent on the direction, or the second is that we have said that the material properties epsilon and the alpha is not function of the direction. If it is not function of the direction, it is diffuse surface. Now we are looking for the more general case, epsilon and alpha when they are equal. So firstly we should introduce the definition of the epsilon. The epsilon is E lambda real surface, D lambda from 0 to infinity, and E black body. And instead of this one I can write epsilon lambda is E lambda real surface, E black body at given lambda. So therefore I can replace this quantity over here, 0 to infinity, E black body lambda epsilon lambda d lambda divided by the E black body. That is the definition of epsilon. Now comes the definition of the alpha. Alpha is the absorbed radiation, irradiation that falls on the body, and from d lambda from 0 to infinity and divided by the overall irradiation. And again I can introduce alpha lambda is equal to g lambda absorbed by g lambda itself, then it will be that 0 to infinity g lambda alpha lambda d lambda divided by g should be equal to alpha. Now I am looking for when epsilon and alpha are equal. I will introduce the first condition. First condition is that if g lambda and e black body lambda are equal, g lambda and e black body lambda are equal, these are equal, and also if g and e black body are equal. Okay, in other words, what I mean is that the irradiation that falls on the object is equal to emissive power of the black body at the same temperature. We are looking for the same T, at the same T. The irradiation that falls on the object is equal to black body emissive power at the same temperature. So for this case, for example, this one enclosure is black body, we have said it, therefore it gives off some irradiation to that object. But this irradiation is exactly equal to sigma to the power of 4. See this condition. And then we have these two terms will be equal, and we will be left with alpha lambda and epsilon lambda. Therefore, in addition, alpha lambda should be equal to epsilon lambda. One of these two conditions should be valid. This is the first case. Or second case is that if alpha lambda and epsilon lambda is not function of lambda, then this term will come to here and that term will come to here. Okay, then the rest will be cancelled out, because I know that e b lambda d lambda from 0 to infinity divided by e black body is 1. This term can be cancelled, and similarly g lambda d lambda from 0 to infinity is g itself cancelled, and it will be alpha lambda and epsilon lambda. And therefore we will add one more condition. In addition, epsilon lambda equal to alpha lambda. Then the epsilon and lambda alpha are always equal, and for if it is not function of lambda, we have said that it is gray surface. Okay, so if we summarize, if the surface is gray, then these are not function of lambda. If the surface is diffuse, okay, if the surface is diffuse, then these two terms are equal. These are equal. If it is gray, then epsilon and alpha are always equal. So if there is gray diffuse surface, epsilon is equal to alpha. So we will look for now diffuse gray opaque surface radiation network, and we have said that if the surface is diffuse, then its properties are not dependent on the direction, and if it is gray, the properties are not dependent on the wavelength, and if they appear at the same time, then epsilon is same as alpha. And if it is opaque, then tau is 0. Then if I write the general energy balance for the diffuse gray opaque surface, I will have some incident radiation, which is called irradiation, and the sum of it will be reflected and the sum of it will be absorbed. So I know also that alpha plus rho plus tau is 1 and the tau is 0 here, and therefore rho is 1 minus alpha. Alpha is same as epsilon, it is 1 minus epsilon. Then if I write the net heat transfer from the body, it will be that the surface area of the body multiplied with the irradiation, the radiosity minus the irradiation, and the radiosity is J is the rho G plus emitted power from the object, it will be E. And instead of rho, I can write 1 minus epsilon into G, and instead of E, I can write epsilon into E black body. Okay, so that will be the definition of the, so it will be J minus G, the definition of the J instead of G. So what we are trying to do is that we are trying to get the similarity between this body and the black body. And instead of G, you can write it as J minus epsilon E into black body divided by 1 minus epsilon. And I will replace this G back to here and to get the net heat transfer from the body and also the radiation network. So it will be that surface area multiplied with J minus epsilon into black body divided by 1 minus epsilon. Okay. And from here you will get AS multiplied with J minus epsilon into J minus again J minus epsilon into E black body. It should be positive because you are subtracting, and divide by 1 minus epsilon. These two quantities cancel out, and the Q dot net becomes the surface area multiplied with the epsilon and the E black body minus J divided by 1 minus epsilon. Okay, so I can write this similarly as a thermal resistance. It will be that E black body minus J divided by the resistance. Okay, and this resistance is called the surface resistance because this is the resistance that prevents the body to become a black body. You can see that this is the difference between black body and some radiosity. Okay, and therefore it will be that the surface resistance will be equal to 1 minus epsilon divided by epsilon into surface area of the body. Some node here, another node here, and then in between I will have the resistance, and the resistance is 1 minus epsilon and the epsilon A into S. Okay, this is always positive. You can feel the epsilon is maximum as 1 here, and then if you write it, you will have the E black body here and the J here. So the reason is that you can see that we have subtracted first from the second from the first, but written opposite here because the heat transfer from the body is taken as positive. Okay, if it is heat out of the body, it is positive, and since it is positive, then it means that this term should be positive here because this derivation is for out quantity. We did not net out. Okay? Because black body emissive power is always greater than the radiosity. That is the reason that we have written it as here. So if this difference is less than 1, then it means that there is heat transfer into the system. That is the reason that we have written it in inverted manner. So if we go back to our black body heat exchange problems, we have said that if it was a black body, say that this one is black body 1 and this one is black body 2, and in between this one is 1, 2, and in between we had one resistance which was R12 defined as 1 by A1 F12, and that's same as 1 by A2 F2 1. But in this case, in the real surfaces, we will add one more resistance here and one more resistance here, and this one will be E black body 2, and this one will be radiosity at 2, and this one radiosity at 1. This one will be black body 1, and here it will be that 1 minus epsilon 1 divided by epsilon 1 into AS, and this part will be 1 minus epsilon 2 divided by epsilon 2 into AS for the real surfaces. Or we can have something like this one, an enclosure, and then similarly you will have, let's say this one is 1, this one is 2, and this one is 3, and you will have 1 and 2 a resistance 1, and this one is the space resistance 1 and 2, and between 1 and 3 you will have again space resistance, between 2 and 3 you will have again space resistance 2, 3, and before that one we will have the black body or the surface resistance. For the 1 you will have the surface resistance, for the 3 you will have the surface resistance, and for the 2 you will have the surface resistance. It will be shown as something like this one. This one will be the E black body 1, and this one will be J1, and E black body 2, it will be J2, and this one is E black body 3, and this one will be J3. Okay, that will be the resistance network, and here we will write 1 minus epsilon 3 divided by epsilon 3 as3, and this one will be that 1 minus epsilon 2 as2, and this one is 1 minus epsilon 1 divided by epsilon 1 as1. Or you can see the same picture here. This one is for the black bodies, and this one is for gray plus diffuse and plus opaque surfaces. Okay, same resistance network here and the same resistance network here. Okay, so we will do examples here and then finish this radiation of the real surfaces.